In this video, we will talk about the completeness axiom for real numbers. We will talk about upper bounds in Suprema as well as lower bounds in Infima. We will talk about the completeness axiom for real numbers, and then the Archimedean property, and then finally the density of rational numbers in the real numbers. We will start with a quick introduction to motivate the completeness axiom for real numbers, and we'll look at the function f of x equals x squared minus 2. And we can see that the graph crosses the horizontal x-axis at a point between 1 and 2. But how can we know there is a number such that x squared minus 2 equals 0? And it turns out if the x-axis consisted only of the rational numbers, then no such number exists. In other words, there's no rational number whose square is equal to 2. But fortunately, our real axis is based on the real numbers. And this completeness, that there's no holes here on the x-axis, the real axis, is what distinguishes the real numbers from number systems such as the rational numbers. We have this quick theorem that kind of goes with this little introduction. The square root of a prime number is not rational. There is a proof here if you are interested. But the idea of this proof is there are many more irrational numbers, like p to the 1/2 where p is prime, or the square root of a prime. That would be irrational. There are many more irrational numbers than rational numbers. So if our x-axis or our analysis was restricted to the rational numbers, then our number line would have many holes where the irrational numbers exist. It is these holes in the number line that the completeness axioms fix. But before we get to the completeness axiom, we are going to talk about upper bound and Suprema. We'll start with the definition of an upper bound in Suprema. So let S be a subset of R. If there exists a real number m such that m is greater than or equal to all elements S in the set S, then m is called an upper bound. Again, m is greater than or equal to all the elements in S. It's an upper bound. And we say S is bounded above. And then similarly, if m is less than all the elements of S, the set S, then m is a lower bound and S is bounded below. And the set is bounded if it is bounded above and below. Another definition, if an upper bound m of S is a member of S, then m is called a maximum of S, and we write m is equal to max S. And if a lower bound of S is a member of S, then it is called a minimum of S, and we denote it min S. These definitions aren't startling, but it's important that you get the difference between an upper bound and a maximum. And the idea is, let's look at an example. If we have a set 2, 4, 6, 8, it's bounded above by the number 8, which is also its maximum value, but it's also bounded above by 9, 8.5, pi squared, because all of these numbers are greater than every element in the set S. But the maximum value of S is 8, because 8 is greater than all the other values in S, plus it is also inside S. So kind of looking at this pictorially, we have the number 2, 4, 6, and 8 that are in our set S. So 8 is the max, 2 is the min, but 8 and above, anything 8 and above could be considered an upper bound. Anything 2 and lower could be considered a lower bound. And remember, upper bounds do not have to be in the set S. Lower bounds do not have to be in the set S. The max and min do need to be an element of the set S. First thing to note, any finite set is bounded and has a min and max. We'll look at this interval, which is not finite because of this open interval, but it's the interval 0 to 8. It is not bounded above because there's no, since the set goes on to infinity, there's no real number that is bigger than every element of the set. But it is bounded below by any number less than 0, because any number, say -2, is smaller than any number in the set. 0 is the largest lower bound, so 0 is the minimum of S, because it is the lower bound that is contained in the interval, and it is the largest lower bound, right? All the other lower bounds are smaller than 0. Describing this as the largest lower bound might seem funny now, but you should get accustomed to that wording. A couple of other notes: the empty set is bounded above by any number and is bounded below by any number. And any subset of a bounded set will also be bounded. So if T is a subset of S and M is an upper bound of S, then M will also be an upper bound of T, and the same holds for lower bounds. And we'll do another example. Find the upper and lower bounds. The max and min of the set T is equal to a rational number such that Q is between 0 and square root of 2. Looking at this interval, 0 is the largest lower bound. In other words, 0 and anything smaller is a lower bound for this set. And 0 is the largest lower bound, and it is also in the set, so it is the minimum T. Here we have 2 and 1/2 is the upper limit of our set, but our set is only the rational numbers in the set, and since 2 and 1/2 is not rational, it is an upper bound, and anything greater than the square root of 2 is also an upper bound, but 2 raised to the 1/2, or square root of 2, is not in the set, so it is not a maximum. So it's not rational, it's not a maximum, but it is an upper bound, and it is the smallest of the upper bound, since any number greater than square root of 2 is also an upper bound. Our next definition is of the supremum. So if we have S is a non-empty subset of the real numbers, if S is bounded above, then the least upper bound of S is called its supremum. So it's the smallest upper bound, and it is denoted sup S. Thus, M is equal to sup S if and only if 1, M is greater than all the elements S in the set S, and 2, if there's another element less than M, then there's some element in S such that that element is greater than our M prime. This is important more if it's an open interval. So we'll look at this definition, or this condition for the infimum on this example because we have an open interval. There's an alternate definition of the supremum. M is the supremum if and only if M is an upper bound, and also if U is also an upper bound, then U is greater than M. So again, it's the idea that it's the least upper bound. Remember, here I have the maximum, which is also the supremum, but there are many other upper bounds, an infinite number of upper bounds as long as you're greater than 4. So again, let's look at this example. Let's say our interval is the open interval at 0 up to and including 4. So there's an infinite number of upper bounds, but the smallest upper bound is equal to 4, and that will be our sup. So here is the idea: infinite number of upper bounds, but the max and the sup are equal to 4. And 4 is also a maximum because 4 is inside the set S. But now let's look at infimum, which is the largest lower bound of S. So it's kind of the same definition, but for minimum. And I have that definition here. If S is bounded below, then the greatest lower bound of S is called the infimum and is denoted inf S. So here, 0, anything less than 0 is a lower bound. But my greatest lower bound is 0. But 0 is not a minimum because this is an open interval at 0. So 0 is not in my set. It's not a minimum, but it is the infimum. So that's the difference between minimums and infimums. And then there's also bounds, lower and upper bounds. There are 3 different things. And here the infimum, that's where we'll look at this condition. That means if there's some other member that is greater than our infimum, then there's always going to be an element S that is in between the infimum and that number that's greater than the infimum, the M prime. So in other words, there's this kind of space so that there's always, no matter how close you want to get to the infimum, there's always some element of S between where you are and the infimum, and that's because it's an open interval. So for kind of an example or exercise, characterize the infimum of S in an analogous way that we characterize this alternate definition for supremum. I have my picture here, where here there's of this interval, that is the closed interval starting at 0 to infinity. There's no maximum, there's no upper bound, there's no supremum. Here, there's an infinite number of lower bounds. Anything less than 0 is a lower bound, and actually 0 is a lower bound, and 0 is the largest lower bound, so that makes it the infimum. And since 0 is also in the set, it is also the minimum. But let's look at this. How do we characterize this in an analogous way? Let S be a non-empty set of R. If S is bounded, then the greatest lower bound of S is called its infimum. Thus M is equal to inf S if and only if M is less than or equal to S for all S in the set S. And if we have an M prime greater than our infimum, so maybe something here like at 1, then there exists some element in S, maybe it's 1/2, such that S is less than M prime. Here's a quick example for you to try. The answers are, in the set 1, 3, the sup is equal to 3 and the max is also equal to 3. Remember, this is just a set of 2 elements. This is not an interval. Here we have the set 1 over 2n, for n is the natural number. So what does this look like? When n is equal to 1, it's 1/2. When n is equal to 2, it's 1/4. When n is equal to 3, it's 1/6. So you can see these numbers are getting smaller. So the sup is equal to 1/2, and the max, since it is in this set, is also equal to 1/2. R in the rational numbers such that R is less than 5. So the sup is equal to 5. That's the smallest, the least upper bound. But there's no max since 5 is not in the set. We went through these definitions to get to the completeness axiom, which says every non-empty subset S of R that is bounded above has a least upper bound. And remember, this applies to every non-empty subset of S of R that is bounded above. It does not apply to every non-empty subset S of R, only those that are bounded above. They always have a least upper bound. They always have a sup. That is, sup S exists and is a real number. And every non-empty subset S of R that is bounded below has a greatest lower bound. It has an inf of S. The corresponding property for sets bounded below follows readily. This is not true of the rational numbers. So this completeness axiom is not true of the rational numbers, which is what structurally sets the real numbers apart from the rationals. So it's this completeness axiom that is that gives us no holes. This is the property right here. If it's bounded above, it has a sup. If it's bounded below, it has an inf. So the completeness axioms answer the question for real numbers. If a set is bounded above, it must have a least upper bound. And recall, we had this example here, which was a set of rationals. This does not have a supremum, if you recall, because the upper bound here, there's no lowest upper bound since the square root of 2 is not a rational. Because the square root of 2 is not rational. It is one of the holes in our rational set. And again, just to warn you, it does not say every non-empty subset of R has a least upper bound. It has to be bounded above. So for example, integers, or the real numbers itself, so the set of integers is a subset of the real numbers, but it does not have a least upper bound, right? If you just take the subset of integers. And that's because it's not bounded above. If a non-empty subset of R has an upper bound to start with, it also has a least upper bound. And to kind of review what we've done so far, we've described what upper bounds were. Those are numbers that are greater than or equal to everything in the set. And then we said that a maximum is an upper bound that is in the set. And then we called the supremum the least upper bound, and the infimum the greatest lower bound. So those are the 6 definitions we need kind of the 3 for the upper bounds and then 3 for the lower bounds. And then this completeness axiom here is what makes R complete. It's that every non-empty subset S of R that is bounded has a least upper bound. It has a sup. And I just wanted to review that because none of these concepts are difficult, but you have to get used to the vocabulary. Here we have a lemma. Assume a real number S is an upper bound of S, the set S, of a subset of R. Then this S is equal to the sup of S if and only if for all epsilon greater than 0, there exists an S prime in the set S such that S minus epsilon is less than S prime. We have a picture here to illustrate what is going on. And just a note, whenever in real analysis we talk about epsilon, usually it's understood that it's a very small number. It's greater than 0, but it's tiny. So the idea is that S is equal to the sup of a set. Let's say we have a set A. So S would be the sup if and only if, no matter how small you choose this epsilon, if you just go S minus epsilon, just something a little bit smaller than S, you'll always be able to find some other S prime that is part of your set S. So it means it's the sup if there's always something, no matter how far, just a little bit of a deviation you go away from S, there's always another element of your set S. It's an interesting little fact. I would definitely keep this picture in mind, and this fact is useful in proving different theorems. And here is a theorem. Given any non-empty subsets A and B of the real numbers, let C denote the set of x plus y, where x is a member of A and y is a member of B. If A and B have Suprema, then the sup of C is equal to the sup of A plus sup of B. So just a little example to see what's going on. If A is equal to 1, 2, and B is equal to 3, 4, then A plus B, if we graphed this out, the smallest number would be 4, and the largest number would be 6. So if I look at the sup of A plus B, that would be 6, which is equal to the sup of A, which is 2, and the sup of B, which is 4. To do this proof, we're going to show two things. To show the equality that sup of C equals sup A plus sup B, we're going to show, one, that sup of C is less than or equal to sup A plus sup B. And then we're going to show, two, sup A plus sup B is less than or equal to sup C, which just leaves us that the equality must hold. We'll start with the first part, which is sup C is less than or equal to sup A plus sup B. And actually, this part is easy because we let AB be an element of C. So AB is an element of C because that's how we defined C. And we know that the element A is less than or equal to sup A, and element B is less than or equal to sup B, which means A plus B is less than or equal to sup A plus sup B. And I was just about to declare victory and say I had shown this, but I haven't quite yet. What I have shown is that sup A and sup B is an upper bound for an arbitrary element, A plus B in C, right? So I've shown it's an upper bound, but I need to know, how does it compare to sup C? Well, sup C is the least upper bound, so sup C must be less than or equal to sup A plus sup B. And I am done. Or I should say I'm done with part 1. So part 2 is sup A plus sup B is less than or equal to sup C. We are going to let A be an element of set A and B be an element of set B, and we're going to consider A plus B. So A plus B, since it's an element of C, is less than sup C. From algebra, I can move the B over. I have A is less than or equal to sup C minus B. Since A is an arbitrary element of set A, then we know that the sup C minus B then is an upper bound of A. By definition of sup A is less than or equal to then sup C minus B. Then we can do the same thing coming back over here to this line, A plus B is less than or equal to sup C, and I can subtract the A, and then I can find that B is less than sup C minus sup A, but B is also an arbitrary element of B, so sup C minus sup A is an upper bound for B, and since sup B is the least upper bound, then sup B is less than or equal to sup C minus sup A. So I sum the results. I have sup A plus sup B is less than or equal to sup A, and then I plug in the sup C minus sup A over here for sup B. And what I get is sup A plus sup B is less than or equal to sup C. And I'm done with my proof. There is an alternate proof here, and the reason why I feel like it's worth doing, it uses this lemma here, which will become useful in other proofs. So looking at this, if we're proving that sup C is equal to sup A plus sup B, so if we want to know something about sup C, we can say an element C, this little c here, is sup C if and only if for all epsilon greater than 0, there exists a little c prime. So we need to show a c prime in C such that our c minus epsilon is less than c prime. So I just reworded my lemma to rename my set S equal to C and my elements little s into little c. Then I'm going to look also at sup A and sup B. So if A is equal to sup A and little b is equal to sup B, then A minus epsilon, that's something a little bit smaller than sup A, cannot be an upper bound since sup A is the least upper bound. Similarly, something a little smaller than B, so B minus epsilon, cannot be an upper bound of set B, right? Because B is the least upper bound of set B. So there's going to exist an A prime in set A such that A prime is greater than A minus epsilon, and a B prime in B such that B prime is greater than B minus epsilon by our lemma. Then A prime plus B prime is greater than A plus B minus 2 epsilon. What we have then is sup C is equal to C, which is greater than A plus B minus 2 epsilon, since C is an upper bound. Then A plus B is less than C minus 2 epsilon, which is less than C for epsilon greater than 0, which means that sup A plus sup B is less than sup C. And that's because, remember, A is equal to sup A, B is equal to sup B, and C is equal to sup C. So this is the alternate proof of the second part of our proof of sup C equals sup A plus sup B. The theorem we just proved is up here along with our two little example pictures, and I have a theorem that talks about functions and sup and inf. So suppose D is a non-empty subset and that F goes from D to R and G also goes from D to R. Then if for every element x, y in D, f of x is less than or equal to g of y, then f of D is bounded above, since g of y is larger than every f of x. And g of D is bounded below, since every f of x is less than g of y. Furthermore, sup of f of D is less than or equal to inf of g of D, which is kind of strange, but the largest, well, actually it's not when you look at this, the largest value of f is going to be still smaller than the smallest value of D. I have my picture of this situation. I have a subset D, and I don't know if it's open or closed, but I just made it half open. And it maps over, a function f maps over into R, so here's my image, f of D. And then I also have G mapping from D to R, and here's my image, G of D in green. And I needed, when I made my image, I needed everything in G to map to something greater than what F maps to. So here, everything in G is greater than that. So again, we know f of D is bounded because everything in G is an upper bound of F. And everything in F is a lower bound of G. So F is bounded below. And furthermore, even the supremum of F, which actually, well, here's the supremum of F is still less than the inf of G, since everything in G is bigger than F. And this picture sort of illustrates this proof of the theorem. That is, if you have a Z in D, and we have f of x, the image of f, is always less than the image of G, then f of D is bounded above by G of Z. And the least upper bound of f of D is no larger than g of z. That is, the sup of f of d is less than or equal to g of z. Since this last inequality holds for all z and d, then also g of d is bounded below by f of d, thus the greatest lower bound of g of d is still greater than or equal to the sup of f of d. We're on our second to last topic, and that's the Archimedean property, and it's such an easy property. But there are a couple of forms, so you need to know an alternate form as well as the super easy one, and it is worth remembering because you will use it in proofs later when we talk about continuity and limits and things. So the Archimedean property is the set of natural numbers n is unbounded above in the real numbers. So the set of natural numbers has no upper bound in the real numbers. Again, that's like so obvious, right? But anyway, we should go on. There are other ordered fields which are not complete. These are the equivalent statements of the Archimedean property, and they don't seem really startling on their own, but they become very useful later when we're doing proofs, and especially part A and part C. So part A is for each z in the real numbers, there exist n in the natural numbers such that n is greater than z. So for example, if z is equal to 3.14, you could say n is equal to 4, n is equal to 5, whatever, anything bigger than 3.14. And the idea is that you can do this no matter how large z is. This part B, for each x greater than 0 and for each y in R, there exists a natural number n such that n times x is greater than y. And last, for each x greater than 0, there exists a natural number in n such that 1 over n is greater than 0 and less than x, no matter how small x is. So x could be 0.001, and then you could say, oh, well, then I just need a larger n, which is maybe 1,000. The proof is fairly straightforward, and we're going to do this proof by contradiction, so we need to see what the negation of this conclusion is, and that would be for all n in the natural numbers, there is n is less than or equal to z. And we're also given that z is a real number. But what this is saying here, for all n is less than z, that means that the natural numbers is bounded above by this number z, this real number z. And then by this completeness axiom, what that would mean is that n being a subset of R and also bounded above, that would mean that n must have a least upper bound. So that's what I wrote here, n has a least upper bound. I am going to designate that least upper bound as alpha, which is the sup of n. And now I'm going to consider alpha minus 1. So it is not an upper bound of n because alpha is the least upper bound. And that means by the lemma here that we had looked at before, assume any real number s is the upper bound of the set S. So now we're having alpha is the upper bound of the set n. Then s is equal to the sup of s if and only if for all epsilon greater than 0. So we're going to take epsilon equal to 1. There exists some element in s, so there exists some n in the natural numbers such that alpha, the sup minus the epsilon, in this case it's going to be alpha minus 1 is less than n. So here's my statement. Again, it comes from alpha being the sup and my lemma, and I'm choosing epsilon to be equal to 1. And then when I look at this, I get that alpha is less than n plus 1, but n plus 1, since n is a natural number, n plus 1 is also a natural number. But n plus 1 being a natural number and alpha being less than n plus 1 contradicts the fact that alpha is the sup, the upper bound of the natural numbers. So that means our assumption was incorrect, and therefore there exists a natural number n such that n is greater than z. The proof of part C follows really quickly from part A, so I rewrote part C over here. For each x greater than 0, there exists a natural number such that 1 over the natural number is greater than 0 and it's less than x. Well, from part A, if we're given a natural number x, then there exists an integer, a natural number n, such that n is greater than x. So again, just from part A, then I can take the reciprocal of each side and I will get that 1 over n is less than x. And when I take the reciprocal, I have to flip the sign, and that's how I get part C. Here's an example. Prove if y is greater than 0, then there exists a natural number n such that y is greater than or equal to n minus 1, or n is less than n. So in other words, if y is a real number greater than 0, then you can find two consecutive integers that kind of sandwich the y. This depends on the well-ordered property of the natural numbers that we talked about for induction. So let's consider the set of all the natural numbers, m, such that m is greater than y. So the set of all natural numbers greater than y. And by the well-ordered property of n, since this is a subset of the natural numbers, then this subset contains the smallest element. We'll call that element n. So then we have y is less than n, since n is part of this set of natural numbers greater than y. And since n is the smallest natural number larger than y, then that must mean y is greater than n minus 1, which gives us y is between n minus 1 and n. Our last topic is the density of rational numbers. So between any two real numbers, there is a rational number. The rational numbers are dense within the real numbers. More precisely, we say Q is dense in R. Sorry, I just said that. Okay, theorem. Density of Q and R. If x and y are real numbers with x less than y, then there exists a rational number R such that R is greater than x and less than y. To prove the density of Q and R, we're going to use this Archimedean property here. So we're going to suppose that x is greater than 0, and here, since x is less than y, then we know y minus x is greater than 0. So now here we have a real number greater than 0, so we should be able to find, and using this Archimedean principle, we're going to be able to find an n, a natural number n, such that 1 over n is less than y minus x. Now we can use algebra to change this to n is greater than 1 over y minus x, and the rest over here is just algebra, so we eventually get ny is greater than 1 plus nx. Now we're going to focus on nx, and since x is greater than 0 and x is greater than 0, then there exists an integer m, or a natural number m, such that nx is sandwiched between m minus 1 and m. And we know that this can be done because we proved that in the previous example. Now I have this inequality. The first part of the inequality comes from this underlined in blue. So I just moved the 1 over, so I get m is less than nx plus 1. This part of the inequality highlighted in green or underlined in green comes from this line here. So ny is greater than nx plus 1. And now I have nx is less than m, which comes directly from here. And then I have m is less than ny, which comes from the line above. So it follows I can divide everything by n, and I have x is less than m over r is less than y. So my rational number is m over n. And you can see that rational number satisfies the condition that it's between x and y. Next, we have the theorem that if x is a non-zero rational number and we multiply that by y, an irrational number, then the product xy is irrational. We will do a proof, which will be a proof by contradiction. Since x is rational and x is not equal to 0, we can represent x as equal to m over n, where m, n are integers and not equal to 0. And we assume that xy is rational. So if xy is rational, then xy is equal to p over q, where p and q are integers. But then y is equal to xy over x, so we have p over q divided by m over n, which is pn over mq. Since these are integers on top, the product is an integer, and it's divided by the product of two integers, which is an integer on the bottom, which would make y rational. And that contradicts our assumption that xy is irrational. I'm sorry, that y is rational, and therefore xy must be irrational. Our next theorem says if x and y are real numbers with x less than y, then there exists an irrational number w that is between x and y. So if you compare this to the density of Q and R theorem, this is kind of like the density of irrational numbers in R. Those are the main concepts. Next, I'll have some problems, some review problems. Here are 4 problems for you to try. Pause the video, give them a try. Also, I will let you know on the next slide, before I have a slide with solutions, I do have a slide with a hint for this last proof. And here is the slide with the hint for the last proof. Here are the solutions to the first 3 problems. I have a couple of notes about this last proof. First, the hint on how to set things up. Once you see how to set it up, it should make sense to you, and so that's something you can kind of learn from, but there's not a lot to explain there. Then the contradictions, how to do the 2 proofs of contradiction. This one's very straightforward. This one here took me a little bit of time, but I have here a summary of everything that was covered in this video, so that there's really not a lot. So just going through each one, I can eliminate everything until I get to density of the rational numbers. And if I look at this first, just each of these different topics we covered. First, we talked about the definition of supremum. So it's an upper bound, and it's the least upper bound. Here we said that x is an upper bound, since x is greater than all the q. And then we said y was the supremum, so y is also an upper bound. Now if I look at my definition of supremum, this m is the supremum if m is greater than all s. So okay, we can say that y is greater than all these q's, and that if we have another upper limit that's less than our supremum, and in here we do have another upper limit x, but x is greater than y. So there's nothing in here that's going to contradict this definition. Also, again, looking at the alternate definition, m is the supremum if it's an upper bound, which y is an upper bound. And then the next part, if u is also an upper bound, then u has to be greater than m. And x is also an upper bound, and x is greater than y. So there's nothing in here in the definition of supremum that's going to contradict x is greater than y. So now let's look at the completeness axiom. So that says every non-empty set S of R that is bounded has a least upper bound, and that is the sup exists. So sort of the completeness axiom, we've already used it. We basically said that it has a supremum. It doesn't say anything about how it relates to x in any other way that we can use it. Next, we can consider the Archimedean property of R. But the Archimedean property talks about how the set of natural numbers is related to R, right? We're talking about having a z in R, and then there exists a natural number. And here, we're really not introducing natural numbers. We're talking about rational numbers. So Archimedean property isn't that useful. We get to the density of rational numbers. Well, now we have 2 real numbers, and then we're talking about a rational number, which is exactly what we have. We have 2 real numbers, and then we're talking about rational numbers. So this is how we got to using the density of rational numbers for this proof. And that is it for this video. Thank you for watching.